The widely accepted explanation for the origin of the universe is the Big Bang theory, which states that initially, there was an infinitely dense mass of matter. This mass underwent a colossal explosion that led to the formation of atoms, molecules, stars, and galaxies, essentially everything we see in the universe today. For decades, this theory has stood as the cornerstone of modern cosmology. According to this model, approximately 13.8 billion years ago, the universe began as an unimaginably hot and dense singularity, expanding rapidly in what we refer to as the Big Bang. This marked the birth of the cosmos as we know it. However, in recent years, research has opened the door to new perspectives that challenge this traditional view. Some physicists now propose that the universe might not have such an early and singular origin as once thought. Instead, it could be part of an endless, cyclical process of expansion and contraction, which might occur in an infinite loop. This idea, often referred to as cyclic cosmology, suggests that our universe goes through repeated cycles of Big Bang-like events, followed by periods of collapse. The implication is profound. The Big Bang might not be the absolute beginning of everything, but simply one phase in an eternal process. Renowned physicist Brian Cox has added another intriguing layer to the discussion by raising doubts about the very premise of the Big Bang theory. Cox questions how something as vast and complex as the universe could arise from nothing, a conundrum that has puzzled many philosophers and scientists alike. This questioning of the origins of the universe challenges the common belief that the Big Bang was the absolute starting point. If the universe did not originate from the Big Bang, then what came before? What was the trigger for the creation of everything we know? These are questions that have led scientists down new paths of exploration and discovery. Adding to the growing uncertainty, recent observations from the James Webb Space Telescope have revealed data that seems to contradict the conventional Big Bang model. While the telescope's primary mission is to look deeper into the cosmos than ever before, its findings suggest that the universe's structure and development may not align perfectly with the idea that the Big Bang was the absolute beginning. These revelations have rekindled one of the most fundamental questions in cosmology: if the Big Bang wasn't the beginning of the universe, what was? Scientists have spent decades refining the Big Bang theory, and it remains one of the most robust models for understanding the universe's early stages. According to the Big Bang model, the universe was once smaller, hotter, and far denser than it is today. In just a few minutes, the explosion that we call the Big Bang forged the basic elements that would later combine to form everything we know, from the smallest atom to the largest galaxy. The theory paints a picture of a universe that began as a tiny, incredibly hot mass, expanding and cooling over billions of years to become what we observe today. One of the most astonishing claims of the Big Bang theory is that the entire universe, every star, galaxy, and planet, was once compressed into a space no larger than a peach. At this time, the temperature was beyond anything we can imagine, soaring to over 250 degrees. Despite the extraordinary nature of this narrative, it aligns well with the observations made by astronomers. From the leftover electromagnetic radiation that permeates the universe to the abundance of light elements like hydrogen and helium, all the evidence supports the predictions of the Big Bang theory. Based on everything we know, this model offers a near-perfect description of how the universe evolved from its earliest moments to the present day. Nevertheless, despite its remarkable success, the Big Bang theory is not a complete explanation. There are still significant gaps in our understanding, especially regarding the first moments of the universe's existence. The challenge is rooted in the limitations of our current physical theories. The combination of general relativity and high-energy particle physics provides a valuable framework for studying the universe, but as we approach the moment of the Big Bang itself, the complexity of the mathematics involved becomes insurmountable. Our methods simply cannot provide meaningful answers about the exact nature of the universe's birth. One of the most troubling concepts in this context is the idea of a singularity, a point of infinite density and temperature. The suggestion that the universe began as an infinitely small, infinitely dense point seems counterintuitive, even absurd. Addressing this issue requires a new approach in physics, one that transcends the limitations of our current understanding. To fully comprehend the universe's first moments, we must develop a theory that unifies all the fundamental forces of nature, including gravity, in the extreme conditions of the early universe. One promising candidate is string theory, which seeks to reconcile gravity with quantum mechanics. String theory offers a potential solution by proposing that the universe's fundamental particles are not point-like dots, as previously thought, but rather tiny, vibrating strings of energy. Within the framework of string theory, the concept of an ekpyrotic universe has emerged. Derived from the Greek word for conflagration or fire, the ekpyrotic model suggests that the Big Bang was not the beginning of everything but the result of a preceding event. This model implies that the universe as we know it is part of an ongoing, cyclical process of creation and destruction. Expanding on this idea, the theory of cyclic cosmology suggests that the universe perpetually oscillates between periods of expansion and contraction. The cycles of creation and destruction stretch infinitely into both the past and future, meaning that the universe has no true beginning or end. This idea is not new. Philosophers and scientists have speculated about a cyclic universe for millennia, but string theory provides a solid mathematical foundation for this concept. One of the most notable proponents of cyclic cosmology is Roger Penrose, an eminent physicist who was awarded the Nobel Prize for his contributions to our understanding of black holes. Penrose was intrigued by a fascinating mathematical relationship between the universe's early, hot, and dense state during the Big Bang and its future state, which is expected to be cold, empty, and devoid of matter. Penrose's theory suggests that, when pushed to their extreme limits, these two seemingly opposite states, the universe at the beginning and the universe at the end, can become mathematically identical. This notion challenges our conventional understanding of time and space, implying that the universe could oscillate between these two states in an endless cycle. While this idea might sound paradoxical, Penrose argues that the absence of matter at the end of the universe could actually give rise to the creation of new matter. In other words, the universe could be reborn from what appears to be nothingness. In this context, nothingness is still something. It is a vacuum that contains the potential for the creation of a new universe. Penrose further suggests that this process might leave behind traces that we could detect, offering a tantalizing possibility for future research. The concept of cyclic cosmology introduces a new way of thinking about the universe, but it also raises profound philosophical questions. If the universe is part of an infinite cycle, how did these cycles begin? What is the origin of the physical laws that govern this process? These questions touch on the deepest metaphysical inquiries about the nature of reality itself. For now, within the realm of physics, we can explore three possibilities for the origins of these cycles. First, there may be no physical explanation at all. The cycles could simply be an inherent aspect of the universe's existence. Second, there could be an infinite series of cycles, each influencing the next in a never-ending sequence. Finally, there is the possibility of a single cycle within a repeating universe, where the beginning and end are interconnected in some as yet unknown way. Roger Penrose's interpretation of quantum mechanics offers another intriguing possibility. In quantum mechanics, physical systems exist in multiple states simultaneously until they are observed, at which point they collapse into a single state. Penrose suggests that each cycle of the universe is influenced by random quantum events, which introduce variations between cycles. This concept opens the door to exciting possibilities for experimental physicists, as it implies that we might be able to detect subtle anomalies in the remnant radiation from the Big Bang, evidence of previous cycles in the universe's history. The exploration of these theories challenges our understanding of the universe, but it also offers exciting new avenues for discovery. Could the universe be part of an infinite loop of creation and destruction? Or is there a deeper explanation waiting to be uncovered? Only time and continued scientific inquiry will provide the answers. What do you think? Let us know in the comments below. If you enjoyed this video, remember to hit the like button, subscribe to Waves Discovery, and share this content with others to spread the word about the mysteries of our universe.